All right, so let's look at number 1, and this is on page 228. Yeah. All right. In one day, a 75-kilogram mountain climber ascends from the 1,500 meter level on a vertical cliff to the top at 2,400 meters. All right, so we got a mountain climber, and then it goes up like this, okay? All right. So this right here and there is ground. This right here, this distance is 1,500 meters. This distance is 2,400 meters. Okay. All right. The next day, oh, by the way, and the mountain climber is what? 75 kilograms, so the mass is 75 kilograms. And so they go from here up to there, okay? All right. Okay. The next day, she descends from the top to the base of the cliff, which is at an elevation of 1,350 meters. All right. What is her change in gravitational potential energy? All right. So she's going to go, and we're going to draw a little cliff there. No, if I do that, it's going to erase the whole thing. We'll just draw a cliff right there. So then she comes back down to here, and that right there is 1,350 meters. Okay. All right. What is her change in gravitational potential energy on the first day and then on the second day? Okay. All right. Well, we know that work is equal to the negative change in potential energy, correct? Okay. Okay. So she started here and she went to there. And this is first day. And this is second day. All right. So we know that negative delta U is equal to what? Well, we know it's U initial minus U final, right? Right? Remember we wrote it U initial minus U final, right? So what was U initial? Well, initially it was what? 75 kilograms times 9.8 meters per second squared times what? Well, Y was what? 1,500 meters? Yeah. 1,500 meters above the ground minus, I'm going to have to drop down here, 75 kilograms times 9.8 meters per second squared times 2,400 meters. And so the change in U, when you do the multiplication, subtract, and distribute the negative, becomes what? 6.62 to the fifth joules? Is that right? So their change in potential energy was what? Positive or negative? All right, where's potential energy lowest? Here or up here? Here. So naturally going up, potential energy should do what? Increase. Correct? Did the numbers come out right? Are y'all checking me on my math now? You need to do this with me. 75 times 9.8 times 1,500 minus 75 times 9.8 times 2,400. Yeah, and then multiply through by a negative. Yeah. So does that make physical sense? Your change in potential was a positive change. It has to be because you're going up higher. Okay, that's A. That's A. That's an A, believe it or not. All right, what about B? All right, 1B. All right, we got negative delta U is equal to what? Well, initially, 75 kilograms times 9.8 meters per second squared times what? 2,400 meters minus 75 kilograms times 9.8 meters per second squared times what? 1,350? And you should get a change in U of what? Negative 7.72 times 10 to the 5th joules. Right? Does that make physical sense? Well, sure it does. Because you got your mountain, so 1,500, 2,400, 1,350. You go from here to there, you're losing potential energy. You're losing potential energy. Come on now, that makes sense, doesn't it? Let me ask you something right now. Which is going to hurt worse? If you lay down on the floor and I hold the rock right here and drop it on your face, or you lay on the floor and I drop the rock from here on your face? Do what? It's going to hurt, yeah. But it's going to hurt a heck of a lot if I drop it from up here. Well, maybe I should have said like right there. It won't hurt too bad. If I dropped it on your nose, it would, but if I dropped it on like your belly or something, of course, everybody don't have a belly like mine. It'd probably bounce up and hit somebody in the head. But anyway, a rock will go, bam, whoa, Mr. Shields, what's going on? All right, now, okay, all right. Well, you might as well laugh about it because, you know, it just is what it is, right? Of course, I'm not proud of it, but still. Okay. Okay. But that makes sense, doesn't it? Sure. You're at a lower elevation. Okay? You're at a lower elevation. Falling off the bed's one thing. Falling off the ridge of the house is a whole different other. You don't want to do that. Okay? All right. Okay, and that was 1B, right? 1A and 1B. Does that make sense? Okay. All right, you want to do one more? What about number... What about number 14? Number 14? All right, we got an ideal spring of negligible mass is 12 centimeters long when nothing is attached to it. All right, so let's draw it here. And it's just hanging there. And so the length of the spring, let's just say Y, is 12 centimeters, which is how many meters? 0.12 meters. Okay, very good. All right. You measure its length to be 13.4. All right, when you hang a 3.15 kilogram weight from it, okay, so we're going to hang a mass is 3.15 kilograms. And now let's redraw it. It's going to do this, isn't it? It's going to go, all right, and then there's the weight. All right, so now this is Y is equal to, this is Y initial, and this is Y final. And it is what? When you hang that mass on it, it goes to 13.4 centimeters. So 13.4 centimeters, which is equal to 0.134 meters. Okay? All right. If you wanted to store 10 joules of potential energy in this spring, what would be its total length? Assume that it continues to obey Hooke's law. So, if we wanted to give it an elastic, and U elastic is equal to 10 joules, all right, what would be its total length? Huh? What is its total length? So at equilibrium, this is Y initial, or equilibrium, E-Q-U-I-L, equilibrium is 0.12 meters. All right, now, that's without anything hanging on it, right? Okay. Are we missing something here? Yeah. Are we missing something here? Do we have a spring constant? What's the spring constant? How do we find the spring constant? Or y squared. We're going to make it y. It's okay, we can do that. So now, spring constant becomes what? That's going to be 2 times the, we'll just say U elastic. Is that okay? Or the work of the spring, work done on the spring. Same difference, y'all, same difference. 2 times that over what? Y squared. Is that right? Okay. All right, so, well, we're going to give it what? Two times 10 joules over, all right, so we give it a what? Now, hang on a minute, folks. At equilibrium, it was 0.12. When we added the weight, it stretched out to 0.134. So which length do we use? In other words, when I added the mass, how much did the spring actually stretch? Point what? 0.01 meters? Yeah. Because look, we're going to say 0.134 minus 0.12, and that comes out to be what? What does that come out to be? 0.13? No. What does that come out to be? 0.134 minus 0.12 comes out to be 0.014. Is that what you said? 0.014? I thought you said 0.14. I'm sorry. So then you do that, and it comes out to be what? 0.014 meters. So we got to plug that in. And the spring constant becomes what? Well, we got 20 divided by 0.014 squared, and wow, you should get this huge spring constant, right? What the heck am I doing wrong? Oh, I'm not thinking. My bad. Oh, I could slap myself. Okay. All right, what force? Oh, I'm doing this thing so backwards. Y'all, I'm so sorry. I'm going to the next step. My bad. Okay. All right. We got to find the spring constant. All right. We don't know how much work is involved to stretch it initially. We know the force of a spring is equal to negative kx or y. Of course, we're going to drop that negative off because that means restoring force. So now we got K is equal to what? The force of the spring divided by Y. And what is the force? It's weight, isn't it? So we got 3.15 kilograms. I'm sorry, y'all. I've solved that completely wrong. Times the gravity, 9.8 meters per second squared, divided by, now we got it right, 0.014. And we get a spring constant of what? It's a pretty big spring constant, 2.21 times 10 to the third newtons per meter. I apologize. Yeah, because that was not the amount of work done on the spring to start with. That was, we're going to store 10 joules. So we have to use gravity, don't we? We have to use the force. We have to use weight. Okay, my bad. Now we can work it. Okay. Now we can use the work equation. U elastic is equal to 1/2 K, and we're going to say Y squared. And so we're going to solve for what? We're going to solve for Y, and it becomes the square root of 2 times U elastic over what? K. So we got the square root of 2 times 10 joules over 2.21 times 10 to the third newtons per meter. And you should get, 9.51 times 10 to the negative 2 meters, or 9.51 centimeters. There we go. Right? So what would be its total length? Okay. Okay. It'll be 9.51 centimeters. All right. Okay? Yeah, always look, if you're not given, everybody listen now, if you're not given the spring constant and the object's hanging, you have to use weight to find the spring constant. You have to do this right here. Look right here. You have to do that right there. And this right here, it can be mg. All right? Okay. All right, we good? Sorry about that. I was getting into the next step. I was looking at it. All right. Okay. Any questions? All right.